is developing an open source LED controller for FIRST Robotics competition. So what is FRC? FRC is the FIRST Robotics competition. It's an international high school robotics competition. Students design, build, and compete with a robot. For our purposes, it's a place with a big frame to put things in, lots of motors and moving parts, and there's a lot of electromagnetic interference. So what is the problem? There's a need for a new discrete LED controller for FIRST Robotics competition. The LEDs make your robot look cool, which is like half the fun, and allow for your feedback to the driver. So if the driver does something with the robot, they know what the robot's doing, if it's doing it, if it's working. We need something that requires minimal communications, bandwidth, and minimal code running on the Robrio, which is the main processor for the robot. I'm sure you can understand why we'd want minimal code. If we're taking up processing time from important tasks for LEDs, that's not great. And preferably, it would be open source and affordable with reconfigurable firmware. If you want your own patterns, who knows? So prior LED solutions were controlling off of the digital I/O port, which takes up a lot of processing time and isn't great. And you have to wire a DIO, which is annoying. Then there was the candle, which is communicates over CAN, and that was not cheap, $60, closed source, and people didn't really love the firmware on that. Then there was a connector X, which is newer, $50, closed source, big, and it can't use CAN, so you have to wire that separately. Okay, why a PCB? Why not just an Arduino? So there's a couple ways you can do things with Arduinos. You could just stick some wires in it and some breakup boards, but those are prone to pulling out. It's really big, and you have to solder the wire. It's just not great. You can also put it on a perf board, which is like a prototyping board. You can break it apart, you can cut it. But that's, even though it's quick to build, it's still not the easiest to solder, and it's still pretty big. A lot of your space is taken up by things you don't need taking up space. Then you can just mount an Arduino on a printed circuit board. This is space inefficient, because you don't need all the parts on the Arduino, and generally it looks something like that. Lots of space you just don't need taken up. So we need to choose a microprocessor. A microprocessor is just a processor that doesn't run an operating system. And we need it to control the LED strip. They're addressable LEDs. You can't just make them do things. You have to send them information. And there's a couple options available for this. Down there, you have like the STM32, the ATmega328P, ATmega328U4, and the Raspberry Pi. I forget the name. But all of these are options available to use as a microcontroller. So USB. This is an important consideration when you're choosing a microcontroller, because you can't just stick USB into a microprocessor that doesn't have it. So you need to decide this before you choose a microprocessor. So it has a number of advantages, which is why it's everywhere. It's easy to program your device. It's easy to debug your device. But it's kind of hard to properly design for it. You need a microcontroller in there that natively supports it. My favorite example would be a U-series AVR, an ATmega328U4. And you need extra hardware to support this. There's also some like limitations on where you can put your USB traces, what you can do with it, because it's kind of sensitive. And signal integrity, yeah, worry. So I abandoned that idea in prototyping. So I landed on ATmega328P, which is the core of the Arduino Uno. There's infinite code out there for it, so that's easy. You can program it through Arduino Studio, which is nice. It has a through-hole package option. This was the biggest consideration. Through-hole is easier to replace. You don't need to surface mount solder, which is annoying. It's better for open source because it's easier to work with. And you don't need any external ICs for the microprocessor itself. You don't need all the bits of it are inside the microprocessor. The biggest drawbacks are no USB support. Arduino Unos have a second microprocessor to do that. It's not particularly fast, nor is it powerful. 8-bit data bus, 16-bit address bus, there's not much on there for code. And it needs an external crystal oscillator to go full speed, which can take up space. And I placed 1.1 and 10 microfarad decoupling capacitors nearby it just to filter out different types of interference. So this is the port I landed on instead of USB. It's the AVR ISP port. It's kind of rare, but it's AVR architecture specific. It's smaller. You don't need any extra hardware, but you need like really annoying drivers. The drivers suck, and it's really slow. It fails like half the time you try and program with it, but it's like nice and small, so that's cool. Differences from Uno. You can see my beautiful drawing of what you don't need on the Uno is in red, and the only things you need are not in red. So you really don't need most of the stuff on the Uno. You don't need USB, you don't need all the headers, and yeah, you lose a lot of the bulkiness of it. And the minimal setup is outlined in documentation. It's pretty much a crystal, something to reset it, and the filtering caps for the crystal. So connectors. Another important consideration, especially for FRC, you have a ton of moving parts in FRC. If you have a bad connector and something falls out in the middle of a match, you can't just fix it. It's a match. So the initial PCB had through holes that were of the wrong diameter, so that was bad. And you don't really want through holes. It requires you to solder. You can't really replace them if they break or anything. So I went with Wagos. Wagos are pretty popular nowadays. They're little wire nuts, and they have their own through-hole PCB-mounted version. So I chose those. They're a little big, like a quarter of the board is them, but they're quite strong. Nothing's going to pull out of them. Other options would be those. They're called wide mullers, and they're really common in FRC, but things fall out of them. And then there's screw terminals, but you have to screw wires in, which is just slow. Okay, CAN. I've been using this acronym a lot. It's kind of a rare communication protocol. It's called Controller Automotive Network, I'm pretty sure. It uses a differential pair signaling method. So if you look down here, you can see what a differential pair is. Any interference is going to, because the two wires are twisted together, any interference is going to affect both wires equally, and then you just invert your low. You invert one of your two wires, which is, you invert it before and you invert it after, and your inversion and then averaging removes the interference. So that makes it extremely robust. It's why it's in your car. So the reason it's in your car is because it's so robust when it comes to interference. It's the most common in FRC, and devices are daisy chained, so you need two ports. Devices have CAN in, CAN out, and any signal goes to everything on the CAN bus. So CAN is not super common. Generally, people buying CAN chips are car manufacturers. So the most common offering for the specification we use in FRC, the 2.0B, is the 2515, which is just Microchip Products 2515. It's just a chip. It's pretty old, and you need a CAN controller connected to it. And then the faster, newer protocol requires a different chip called the 2517. But that's only available in surface mount. So again, bad for open sourcing if it's hard to make for other people. So I landed on the 2515 and the 2561. The numbers don't matter. I just landed on those, cheap, compatible. FRC has its own idea of what you should be doing with the CAN bus. So they take the extended ID. Every CAN packet has an ID and then the data. They take the ID and they break it up into chunks down here. Most of these chunks don't matter. The device number is unique for every single one, no matter what the first bunch of bits are. And so presumably, you could just filter by device number. And you know the main processor was sending you data by just filtering by that. You could just look for your device number and you know. Unfortunately, they decided to not do that. They put a very important packet called heartbeat. And they gave it an ID of 0. And literally everything has an ID of 0. That's important. So if you try and filter by that, you're going to get a bunch of junk. So it also requires just tangential, requires you to shut down. So another capability our thing needs. So the library I use has masks and filters. This is a good representation of it. A mask is going to tell you what bits matter. A filter is going to tell you what value those bits should have. And if it doesn't meet one of those two requirements, it discards it, which keeps it fast. You aren't filling up registers with things you don't care about. So again, mask designate which bit matter, specify which values of the bit matter. Take some testing, because CAN is weird. Sometimes there's just weird stuff. Sometimes your masks don't work. And then you also have to make it shut down, which required some messing around with the masks and filters, because that's over the heartbeat, and that has an ID of 0, and we really don't want anything that isn't important in our registers. So power supply. FRC uses motorcycle batteries. That is a motorcycle battery. 12 volt, everything. There is a module that converts it down to 5 volts, but that requires extra wiring, and it takes up space that really isn't necessary. And then it would be nice if on my thing, there was reverse polarity protection, because like, what if there's a short? What if we mess something up? Best if there's protection for that. Quick explanation of capacitors and inductors. I'm sure some of you already know this. Capacitors pass changes of voltage and block constant voltages. Inductors pass constant voltages and block changes, which matters because we need to filter our 12 volt in. So capacitors, we have capacitors between 12 volt and ground to pass any changes, and an inductor placed in series to make sure no changes get through, because we want a stable power source. Inductors use magnetic fields, not great for electromagnetic interference because it's a magnetic field. And I made a mistake. You're supposed to use a choke, which has a metal core, and not just any inductor, and I used a generic inductor. That's not great. Anyway, you can see the power supply filtering there. Pretty simple. So the power supply IC, this one was weird. There's plenty of options here because a lot of people need to take 12 volts and turn it into 5 volts. Preferably, I would prefer if I had something that was small and gave me 5 volts, 1 amp, so I came upon this. It needs some tolerance. FRC uses motorcycle batteries, which means your power supply will droop if you are, if you have high load current, especially when you're moving the motors. It can get all the way down to 7 volts without browning out, so it needs to be able to handle that. And it's frequently over 13 volts at full charge, so you can't have something that only wants 12 volts. So this one seemed like a good idea. Small, high efficiency. It could take 7 to 36 volts. And it can have a common ground. 5 volt and 12 volt can have a common ground, which makes it just easier to design. I don't need to isolate my 2 grounds. And then I connected it through a Schottky. A Schottky diode is just a diode that doesn't have a ton of forward voltage drop. So good for protection. The issue is that it likes to get hot, like really hot. And it has a plastic case, so you can't like put a fan on it. So it doesn't seem to like melt the board, and it doesn't seem to melt itself, but like it gets really hot, and it's not good. And it could be harmful. The solutions aren't great because it has a plastic case. You aren't gonna like put a heatsink on a plastic case. So layers, this is another important design consideration when you're designing something with a PCB. You have to decide how many layers you're gonna have pretty early on. So you have layers, you have copper's your conductor, so you have copper and then plastic and then copper and then plastic. And you can, generally the 2 options are 2-layer, 4-layer. 4-layer is more expensive, it just costs more to make. But 2-layer is harder to route because you only have 2 layers to route on. So if 2 things cross or 3 things cross, you have to figure that out without, like you can't just put it on a layer below it. And then also you can have a separate power ground plane. That's really good for signal integrity because it's just bigger. You don't have, interference is just reduced, and the loop inductance is reduced as well, which is very nice. And you can separate your data lines, that's nice. So this is the big advantage, ground plane. 1 whole layer can be ground on 4-layer. Generally, you're not gonna do that on 2-layer. You'll see why in a second. And it improves your signal integrity, and it takes full advantage of your copper pore. You get an amount of copper, and whatever copper you don't use is just, you paid for it, but you don't get it. And in the first iteration, it was just a trace. It just ran throughout the board. It wasn't great. That was pretty bad for EMI. In the revision, I made the second layer of the design mostly ground plane, which was bad. That was a bad idea. Gaps in the ground plane are really bad. They cause a ton of loop inductance, which means it acts like well, it has inductance, it's active, it resists changes in current, which is horrible for signals. Especially high-speed signals, which I ran right over 1, which means even worse. And then really big gaps, like the one right there, like everything that's not blue is a gap. Like the blue, the black parts are gaps. That really big long one at the bottom is acting like a massive antenna, which is super, just horrible idea, horrible idea. Powering the LED strip, pretty simple. It just wants 5 volts. The data sheets do call for a 1,000 microfarad capacitor between power and ground unit, but that's pretty simple. You just put it on there. Signal integrity isn't bad. Digital's pretty good for that. Only 2 spots it can be, so you need a full 5 volts of interference to really do anything. And you get a bunch of libraries for it, so nothing to worry about there. Crystal oscillator is a pretty common component. They just generate a sine wave with some feedback. 2 necessary. This is what I routed the traces for this over the ground plane. That's why it's so bad. It's 16 megahertz. It changes. Yeah, it's not good. And I just need to keep them away from 12 volt. Any big interference on these can really mess up the microprocessor. Extra features I did. So for terminating CAN, you need to bridge the 2, CAN high and CAN low, with a 120 ohm resistor. So you can do that by just soldering in a header and popping I forget what you call it, like a little shorting thing on there. And you can solder, you have an I2C port. So if you want to put something else on there, if you want to have more things on your robot, you can do that. And there's a solderable jumper to standby on the 2561 to ground. The biggest issue on the first run through of PCBs was that I forgot to connect standby, so it just didn't work. So now you can just short it to ground if you really want. There's a schematic, not super informative. You can see the chips I'm using, and you can see the over there on the left. You can see the power the filtering for every chip, but generally you're not going to derive much from that. There's the full layout of the second of the revision. Pretty dense. There's a bit of wasted space, but that's mostly because of the size of the connectors. Nothing terribly interesting. Of course, you can see the ground plane gaps, which isn't good. There's the first PCB. It's really space inefficient. I didn't compress anything down. I just let it's pretty sprawling. And you can see that I didn't solder a ton on there. This is like minimal setup to get it working. Unfortunately, it didn't work, so I went with my second revision. There's the unassembled, and there's the mostly assembled. I left out the extras because we didn't need them. Pretty good. You can see that the Wagos take up most of the board, which isn't great. And there's a pen for scale. It's reduced in size by like a couple of millimeters. Shortcomings. LED strips turn out to really like current. So I should have gone with a 2 amp converter, not a 1 amp one. That was really bad for the amount of LEDs you could use. The board is overall just really big compared to, in particular, the CAN LED, the more expensive alternative. And that's because of the Wagos. If I didn't have the Wagos on there, that'd be nice. Mounting holes would be useful. You need to mount things in FRC. You can't just let it dangle. So no mounting holes is kind of annoying. You have to like tape it down. And then the ground plane gaps. I should have gotten rid of those and just used a 4-layer board. Pricing was fine. So PCB manufacturing was $3.20. JLC PCB gives you like a ton of discounts. You don't really need to pay that much for those. But the most expensive components were the Wagos. That was $25. They were half the entire price. That was really bad. Like connectors aren't even that important, and I let them inflate to that big of a. Yeah, that was bad. Not horrible. It's priced similarly to the Connector X, which is our cheapest commercial option. And yeah, check your component prices before you design the board. Upgrades. The 2515 and 2551 are old, like really old. They're like 2000s old. And you can combine them into one chip. It's called like the 25651, which is just smaller. And then you can also, the alternative to the new central processor for FRC, well, not the alternative, the new central processor for FRC just uses natively the faster CAN protocol. So you need to support that to get full speed. So that has to be swapped out with these newer chips. So that's in like 2 years off to, if I want to use this board, I have to swap those. Wago connectors are huge. I should have replaced them with something more common. And I could move from through-hole to surface mount. Through-hole is really big. It takes up a lot of space. Most of the chip is just empty. So that's kind of pointless. I probably should have gone with surface mount, but again, it's harder to solder, a little bit harder to design for sometimes. And the 328P isn't super powerful. If you want to do if you want your LEDs to do something weird, if you want them to have something cool on them, the 328P isn't necessarily going to be capable of doing that. So I could upgrade to something stronger to use more complex LED patterns. Conclusion, all files are available on GitHub on that link. Project was overall a success. It controlled LEDs, which is all we really needed it to do. It can control like 70 or something, which is probably more than enough for any robot, unless you like drape them on it. We plan to use it on our competition robot this year as Team 2404, and kind of gonna get on my soapbox here. FRC, like, teams really like to just buy. Like, they will buy anything. If you put it on sale, they will buy it. And it's all closed source. So all of the software for FRC is free and open source, but all the hardware is closed source and expensive. FRC could really use some electronics design instead of just wiring. Most of FRC electronics, you just wire things together, which isn't great for high schoolers because that's not applicable. There's plenty of people who can wire. And hopefully this inspires other teams to design their own custom circuits to fulfill problems instead of just buying expensive alternatives. All right, thank you. All right, Q&A. We have...
All right, so stick around for a Q&A. Make sure to just stay in your seat and raise your hand, and we will be passing out the microphone so that Conor here can answer your question. But we do still have plenty of time in this block of time. So let's just bring out the first person.
Great talk, thank you. A quick question, why did you need external chip to do the CAN interface? Couldn't you do like a software bit banging or something like that on your ATmega? Because you don't need a very fast communication, I'm guessing, to set your LEDs.
Are you asking like, why do I need chips to interface with CAN?
Right. Couldn't you use some of the I/O pins on your ATmega and do some bit banging software solution to emulate the CAN?
You theoretically could. Generally, the speeds are too high. It's 1 megahertz, and the problem is you're getting so many messages, you have to store them somewhere. So that would pretty quickly fill up any storage on. Like the ATmega 328P doesn't have that much storage for that. And also, it's a differential pair, so you need something to do the differential pair thing, or else you lose the main advantage of CAN. You need something to invert and then to average the two voltages. Which is relatively difficult to design. I suppose I could have designed something to do that, with diodes, but it would be generally bulky and it would be kind of annoying to build for other teams. Generally, you want an external chip for CAN. Yeah.
Any other questions? Over here.
You're still 2404 or you're graduate?
Hmm?
Are you still 2404 or are you graduate?
Oh yeah, I'm a junior. I'm in 24. Yeah.
Okay. Right. Yeah.
Okay, once again, you're still with 2404. You said you're a junior. Surface mount soldering could save you a lot. It seems complicated. There's organizations that do that sell some small, fairly cheap, like learn to solder kits that are specific for learning to solder surface mount. Bonus, 2404 is local, right? Like near Pasadena? Or
Yeah, we're in Pasadena.
Okay. Don't know if you're aware, there's another conference called Layer 1 that's held down the street at the Hilton. There's always a hardware hacking village. There are always people there that are happy to teach you how to solder surface mount. If you want to move forward with the design, that if you got the time, it's usually over Memorial Day weekend. It's an opportunity to learn and maybe rev the design if you feel like it. But the question I had is, did you consider, instead of using the expensive real estate gobbling Wagos on the board, why not do a pigtail with maybe a cheaper connector, just Molexes?
I did consider it. So Wagos are like the new thing in FRC.
Right.
They're putting them everywhere, and I was a little worried about using something a little weaker, because this is probably, because it's discrete, the whole point is you can put it somewhere else. This is probably going somewhere, like we're going to have LEDs on the arm, this is going near the arm. I was worried about it pulling out. Of course, in hindsight, that was a dumb idea. I should have just gone with a Molex. Definitely a design regret is using Wagos. price and size were just not worth it. But they are good connectors in every other regard. It's
Absolutely.
just, yeah. All right, thank you for the advice.